So now I have my two capacitor equations, the two forms of the equation. One is I in terms of V, and the other is V in terms of I. And we're going to basically look at this equation here and do a little exercise with it to see how it works. I'm going to draw a little circuit here. And it's going to have a current source and a capacitor. The value of the capacitor is 1 microfarad. And the value of our current source, we'll call it big I. And it's going to actually look like a pulse, like that. That will go from 0 to 3 milliamps, and then back to 0 over here. And the amount of time it takes, that's going to be, this time here is going to be 3 milliseconds. And the question I want to answer is, what is V of t right here? We're going to use this integral equation to figure that out. So over here is where we're going to put our answer. This is going to be t, and this will be I. Here's I. And our plot right down here will be t, and here's V of t. We'll plot I this way on here in time. It's 0, and then it goes up to some value, and then it goes over. So it's a pulse of current. And we said that that was 0. This is 3 milliamps. And this is 3 milliseconds. And now what we want to do is we want to find V of t. One of the things we have to do, we have to make an assumption about V naught here. And we're going to assume for our problem here that V naught equals 0 volts. And what that means is there's no charge. There's 0 charge stored on this capacitor when we start the experiment. So now let's look at 3 different time periods. Let's look at the period before the pulse, during the pulse, and after the pulse. So we'll break the problem into 3 parts. Part 1 is before, and we'll do that by just looking up here. Now we decided that V naught was 0 in the before state. So we'll put a little 0 there. We decided that I is 0. So that means that the term inside the integral is 0. And what that means, 0 plus 0 is equal to V of t. So before the pulse, the capacitor equation tells us the voltage is 0. Okay, now let's go during the pulse. Let's do the second period of time. Let's do during the pulse. So now we have to be a little more careful. We have V equals 1 over C, integral from now time equals 0 to time equals some time t. And what's I during the pulse? What's sitting right here? I is a constant. So we write in 3 milliamps d tau plus, don't forget the starting voltage. What's our starting voltage? Well, we look right here, and the starting voltage is 0 plus 0. So now we can solve this. V equals 1 over C times 3 milliamps comes out times the integral from 0 to t of d tau. And that equals, let's plug in C this time, 3 milliamps divided by 1 microfarad times, what does this evaluate to? The integral from 0 to t of d tau is just t. Let's do a little bit of arithmetic here to reduce this. Milliamps is 10 to the minus 3, and microfarads is 10 to the minus 6. So let me move this up. We'll keep our plots on there. And what we end up with is V equals 3, 10 to the minus 3, 10 to the minus 6, so that's 3 times 10 to the third, or 3,000, times time. And what's that? That's the equation of a line. And it has a slope of 3,000. What's the units here? This is 3,000 volts per second. And so I'll go over here and we'll sketch this in. This is going to be a line that's a straight ramp with a constant slope, like that. It's going to be happening all during this pulse. And we can ask, what's this value right here? What's that voltage right there? Okay, let's work that out. T is 3 milliseconds. So let's plug in 3 milliseconds right here. So V at 3 milliseconds equals 3,000 times 3 milliseconds. And that equals 3 times 3 is 9. And 3,000 times, this is an exponent of minus 3. So it's going to be 9 volts. So this value right here, right there, is 9 volts. So that says the voltage on our capacitor during the pulse, during the current pulse, rises in a straight line up to 9 volts. And we got that from this integral that we did. The capacitor is integrating the current, adding up the current. It's integrating this pulse to get an ever-rising voltage. Okay, so now we've solved the capacitor equation during the pulse, and let's go back now to what happens after the pulse. And we'll do that over in the corner over here. So now let's solve what happens. Let's solve what happens after the current pulse. What happens to this voltage from here on? Does it go down? Does it go up? Does it go straight sideways? Let's find out, and let's use our capacitor equation to do this. So now what we're doing is we're going to do a new integral, and we're going to start at time equals 3 milliseconds. And what is our voltage at 3 milliseconds? What's V naught? So V naught, in this case, equals 9 volts. That's for this period of time after 3 milliseconds. And we'll use our equation again. V is 1 over C times the integral of I of tau d tau plus V naught. All right, so and it goes from time 3 milliseconds to time t. So time t now is out here somewhere on the time scale, and we know the voltage right here. We filled it in. There's the voltage right there. We're going to fill that in, and we're going to work out what's the voltage out here after 3 milliseconds. So to solve this integral, we look and say, well, what's I of tau? What's I of tau during this time? Let's look at our chart. The pulse is at 0. Oh, look. So this whole term right here, this entire term right here is 0. And what is V naught? V naught, we decided, was right there. V naught is 9 volts. That's where we started from. And so the answer here, after the pulse goes away, is V equals 9 volts. And I can sketch that in up here, and basically it just goes straight sideways at the new voltage. So that's how we solve a capacitor problem, a really simple one. And it happens that we were integrating a current pulse, and what we got was a voltage ramp.